Hi everyone, welcome to another video for Research Design and Analysis. This is our second video where we're going to be talking about multi-way factorial analysis of variance, which is another way of kind of talking about when we have models with multiple categorical predictors. So this is following up on our previous video where we introduced where we have multiple categorical variables that each have multiple levels. But in this video, rather than focusing on how to code those variables and how they look in the regression model, we're really going to focus in detail on how to create that factorial analysis of variance table and calculate the different F statistics that we need to do our statistical analysis. So as a reminder, we had this hypothetical example where we had a 2x3 factorial ANOVA, where we had diet, which was a categorical factor with 2 levels, and exercise, which was a categorical factor with 3 levels, which ultimately meant there were 6 total groups that we could randomly assign individuals to, right? We have 6 groups because each level of diet is represented at each level of exercise and vice versa. So in this model, we need to be able to account for the main effect of diet, which is to say, what is the effect of diet on average across levels of exercise? What is the main effect of exercise, which is the effect of exercise on average across all the different diets? And then is there any evidence of a diet by exercise interaction? And again, that interaction tells us, does the effect of diet depend on the level of exercise? Or conversely, you could also talk about that interaction as, does the effect of exercise depend on your diet? Either way you state that interaction would be correct because they mathematically work out to be the same, right? The interaction is just saying, does the effect of one of our variables depend on the level of the other variable? And you can refer back to our previous video for how we constructed this model, but remember that we're making some prediction based on a number of contrast-coded variables where we need one less variable than the number of levels of that categorical factor. So diet can be represented with 1 variable, exercise has to collectively be represented by 2 variables, and the diet by exercise interaction is represented by 2 variables here because it is the product of each of our contrast-coded variables for each of those independent effects. So we have 2 for exercise multiplied by 1 for diet, so we ultimately need 2 contrast-coded variables to represent the diet by exercise interaction. So when we're building this analysis of variance table, it's really pretty much the same as analysis of variance tables we've built in the past, where we're going to have the sum of squared errors as kind of our starting point, and we're going to start with the total sums of squared errors in Y. Then we can work out the sum of squared errors explained by the regression and the sum of squared errors that are left over in the residuals. The only difference here and where this gets more complicated is that now we have to break apart the sum of squared errors explained by the regression into a number of different sources. So we're going to have some that's explained by diet, some that's explained by exercise, and some that's explained by the diet by exercise interactions. And we're going to work out how to fill in these sums of squared errors, and then we're going to work our way across the table from the left in order to calculate the F statistics and then get the p-values for all of the different statistical tests we might want to conduct in this situation. So first, let's start by calculating the total sum of squared errors in Y. In this example, it happened to be 1010, and we can get a degrees of freedom here, which is n minus 1, and we had 18 observations in this data set. And n minus 1 is it's n minus the number of estimated parameters. And remember, to calculate the sum of squared errors, we need to make an estimate of the population mean. Because to calculate the sum of squared errors, we need to look at each score minus the mean. So we're estimating 1 parameter. So the degrees of freedom for the sum of squares total is always going to be n minus 1. But conceptually, right, it's n minus the number of estimated parameters. Next, we can calculate the residual variance, right? What is left over after we've fit this regression model. So to calculate the sum of squared errors of the residuals, right, we need to calculate our prediction for each Y value based on the equation up here. So we're going to find values for each of these betas, right? And then depending on what group you're in, we'd plug in the appropriate values for the X's. We would multiply the coefficients by the contrast-coded values, right? And then we would add everything up and we'd get some Y prediction. And then we would say, how far off of your actual Y value was our prediction? We'll square that difference and get the sum. And then that will tell us, after accounting for everything in the model, how far off was our prediction. So in this case, we happen to have a sum of squared errors of 50 for the residuals And we have a degrees of freedom of 12 here, where again the degrees of freedom are n minus the number of estimated parameters, but the number of estimated parameters here is actually going to be 6, because our prediction is based on all 6 parameters in this full model. So we have an intercept plus 5 slope coefficients here in order to generate this predicted value of y. And then we're going to look at the difference between that y prediction and the actual y value. So to calculate the sum of squared errors of the residuals, we're actually estimating 6 total parameters. So 18 minus 6 is going to be 12 in this situation. Now, to calculate the sum of squared errors explained by the regression, we have a few different ways of calculating that. The first is just to remember SS for the regression is SS total minus SS of the residuals, because this value and this value have to add up to the total value. So you could just do that by subtraction to figure it out. But the other way you can think about it is we actually are going to generate our model predictions again and compare those to just the mean value of y, right? And say, well, how much different are our predictions than the mean? Because remember, under the null hypothesis, all of these coefficients should be 0. And the only thing that we need under the null hypothesis is an intercept. We should just predict the mean for everybody. So we want to see how different our predictions are from the mean, and then we'll add up all those deviates, we'll square them and then add up all those squared deviates. And in this case, that adds up to 960. And it has 5 degrees of freedom here, because again, it's n minus the number of estimated parameters, but the number of parameters needed here are 5 because it's the parameters that we're testing in this model, right? To get y hat, we need to use 6 because we have an intercept plus the 5 slope coefficients. But to get y bar, right, to get the average y, we also need to estimate a parameter. So we're basically comparing a model that, our full model has an intercept, right? And we're comparing that to a null model that also has an intercept. The difference is the null model doesn't have any of these slopes. So the number of parameters that we're testing are the 5 slopes because the intercept is common to both models. And you can refer back to our previous video if that's a little bit confusing, but hopefully it makes sense why the number of tested parameters here is 5, but the total number of parameters that goes into this degrees of freedom down here is 6. So next, right, in much the same way we calculated the sum of squared errors for the regression for the full model, we can break that up and calculate it for each of these individual components. And we can say, okay, out of that 960, how much was explained by diet, how much was explained by exercise, and how much was explained by the diet by exercise interaction. For the effects of exercise and the interaction, we can even take that a step further, because remember, exercise is actually made up of 2 contrast-coded variables. So if we just want to talk about the main effect of exercise, that's an omnibus test of both predictors at once. So we'd have 2 tested predictors here. But if we wanted to drill down a little further and say, well, is it the linear contrast or the quadratic contrast that's doing most of the work? We would have to then do tests of these individual contrasts to see which one is statistically significant. Similarly, for the diet by exercise interaction, right, that requires 2 contrast-coded predictors. So there's going to be 2 tested parameters there. And we'll get a total amount, and we can say, oh, overall, is there a statistically significant interaction? But then we can drill down a level further to say, okay, well, what about the linear interaction versus the quadratic interaction? So because each of these are made up of multiple contrasts, they're going to have increased degrees of freedom here, whereas for the effect of diet, that only takes 1 variable, so we just need the 1 variable there. Next, we'll need to calculate the mean squared error for each of these terms, which once we have the sum of squared error and the degrees of freedom, that's really easy to do because it's just the ratio of those 2 values, right? I take the sum of squared errors, divide it by the degrees of freedom, and that gives me the mean squared error. And what the mean squared error, right, is telling me is per parameter, how much variance have I explained in the case of all the things in my regression model, or for the residuals, it's per parameter, how much variability could be explained, right? So this is essentially how much variance would we expect to explain for a single parameter, and then this is how much variance did we explain for a single parameter up here. Once we have those mean squared error values, then we can take the ratio of the mean squared errors explained by that effect relative to the mean squared error of the residuals. So for instance, to get this first one, we do 192 divided by 4.2. That works out to be about 46.1. Because on average, right, for our 5 parameters in the full model, we explained about 192 squared errors per parameter. And based on the residual variance, we would expect to explain about 4.2 squared errors per parameter. So that is about 46 times greater than the residual variance. And therefore, this is likely going to be a statistically significant F value because it is unlikely to occur under the null hypothesis. And we're gonna calculate those p-values in a moment. But that's a pretty big difference, right? So remember that the F ratio is the F statistic is a ratio of the variance that we explained per parameter relative to the variance that remains to be explained per parameter. And if that's a big number, then that means we explained a lot, and that's kind of surprising if the null hypothesis were true. Once we have those F values then, right, again, we will usually let our computer do this for us, but we could calculate the probability of it observing an F this large or larger under the null hypothesis. And assuming that we get a really small F value, that is statistically interesting. And we would say, okay, this is pretty unlikely to have arisen under the null hypothesis. Therefore, we would reject the null hypothesis in this situation. It seems like sampling variability alone does not explain the differences that we saw in our data. And we're explaining a lot more variance than we would expect, kind of just due to chance. So we think that, well, perhaps there is something systematic going on here. Now, for the test of the full model, that doesn't tell us a whole lot because we just say, okay, as a set, we've explained more variance than we thought we would due to sampling variability alone. But it doesn't tell us, is it diet, is it exercise, or is it the interaction? So although this Omnibus F test of the full model is interesting, we're really probably going to focus on the F values for these individual effects. So we might want to look at, for instance, the main effect of diet. And it actually has a statistically, very interesting F value here because the p-value is so small. So we'd reject the null hypothesis and say, well, something in our outcome is explained by diet. Similarly, for exercise, right, it's going to be a statistically interesting result because the p-value is so small. And we'd say, well, something in our outcome is explained by exercise. But we also have an interaction that has quite a small p-value. So we would say, okay, we also have some evidence that the effect of exercise depends on what diet you received, right? So, but each of these statistical tests has a slightly different interpretation because the Omnibus F for the full model, right, tells us how all the parameters are doing as a set. The Omnibus F for the main effects of diet and exercise tell us about how diet is doing on average across levels of exercise. Exercise tells us about exercise on average across levels of diet. And then the Omnibus F test for the interaction tells us, does the effect of diet depend on exercise? And it looks like we have some evidence that it does. Now we have a couple blanks here, right? Because inside of these omnibus tests, we could do individual comparisons. Because in much the same way that the full model doesn't tell us which parameters are explaining variance, the Omnibus F test doesn't necessarily tell us, for like exercise, for instance, is it X2 or is it X3 that is really explaining the variance? So in the face of these statistically significant omnibus tests, we'd likely have to do some post hoc tests to determine which individual contrasts are statistically significant. So if we, following those statistically significant omnibus tests, right, we could then fill in for the F tests for each of the individual contrasts and similarly get the p-values for those. And for instance, looking at the effect of exercise, we can see that the effect of X2 gave us a very large F value. So it seems like there's a pretty big difference between low and high exercise, and that led to a very small p-value. However, for the quadratic effect, the moderate exercise group didn't really deviate from the mean of the low and the high exercise groups. So there's not really much evidence for a quadratic effect here. And there would be different ways to do these post hoc tests, and in other videos we'll talk about kind of strategies for doing that post hoc testing. But the main thing is that you want to look at your Omnibus F test first, and generally if the Omnibus F test is yielding a very small p-value, that means something systematic is going on with that variable, and that warrants further exploration. And you can figure that out then exactly what is happening by looking at your individual contrasts, or by doing things like individual t-tests to compare the individual groups and say which one is different from the other one. Finally, the last thing that we can do is calculate standardized effect sizes, or the related eta squared, or indeed this is actually something called a partial eta squared for each of these individual effects. But we're going to talk about these at length in another video. So keep in mind that these are standardized effect sizes here. So these are going to be common in a lot of statistical programs and outputs, but we're going to dedicate another video to those.